Okay, let's go ahead and get started. So this is day 7, and we're going to talk about chemical reactions. So yesterday and last week, we've been talking about bonds, and you guys did great on the problem set that you all turned in last night or this morning. There's still a little bit of confusion on line drawings, which is totally okay. I think that's one of those things that you just practice and eventually it sort of sinks in, but I'm happy to go over that more. Feel free to stay after class. I think there's a few of you that I've talked to about reviewing it more after class. So today we're going to talk about chemical reactions. So the sort of technical definition that I pulled from a textbook is one or more substances are converted into other substances. So basically we're turning stuff into other stuff. And just some sort of words and definitions. Reactants are what we start out with. These are the things that are going to react with each other. And then products are what we end up with. So even if reactants isn't sort of an easy word for you to remember, products is what we end up with at the end. So I think that one should be a little more intuitive, and then reactants are, the other one. So when we're writing a chemical reaction, we write it as reactants going to products. So the arrow tells us which direction the reaction is going in. It's starting with reactants and going towards the products. So for an example, in sort of daily life, flour, yeast, and water reacts to make bread. That reaction requires heat. I need to put it in my oven. And so we denote that with a little triangle that goes on top of the arrow. I remember that because to me, it looks like a tiny little fire. I don't know, maybe I've just like justified that to myself. But the triangle means that there needs to be heat for this reaction to proceed. And then the last thing is that the arrow indicates direction, like I was talking about. So this reaction is irreversible. That means I can't reverse it. It can only go from reactants to products, but once I have the products, I can't go back to the reactants. So using that bread example, I can take flour, yeast, and water. I can add heat and do some other stuff and get bread at the end. But once I have bread, I can't go back to flour, yeast, and water. The yeast is dead, everything, I've got a totally new thing, I can't go backwards. Some reactions are reversible, and so we would denote that with an arrow that has 2 faces. So that means I can go in either direction. Does anybody have any questions on just what a reaction is, what are reactants, what are products, what these arrows mean? Okay. So just to get practice thinking about this, this is something you might sort of get in the habit of doing long term, but I'm gonna put you in groups and I want you to think about a chemical transformation that you might see in your daily life. So that bread example maybe, or you breathing, or any sort of chemical transformation that you see. And then think about how chemists would describe that. What are the reactants? What are the products? And how would you write it? Where's the arrow? Which direction is it going? Does it require heat? So just sort of think of any reaction. And like I've said before, I think half the point of prep is getting to know each other and learning how to collaborate together. So I'd highly encourage you, if you can, to turn your camera on and actually talk to each other. So I'll give you like 5 minutes to chat about it in your groups. And so I'll pull you back at like 10:50. Okay. So go ahead and accept those breakout rooms if you haven't already. I'm going to pause the recording so that those who are watching later don't have to stare at my face for 5 minutes, but I'd highly encourage you to, if you're watching this later, pause the video, look around your room wherever you are, see if you can come up with the reaction that you're seeing. Okay, I'll just give it another 15 seconds for everybody to come back in. Okay, I think everybody's back. So does anybody have a chemical transformation or a reaction that they'd be willing to share either in the chat or go ahead and unmute yourself? Yeah, go ahead.
I said an egg. Like, you know, you put like, I don't know, like the chemical composition, you know, is there even a chemical composition for an egg? You know, I don't even know, man. But egg, salt, and like oil or something, right? What even is oil? And then add fire, and then you can cook the egg.
Exactly. So that needs heat. And so we'd put a little triangle on top of our arrow to show that we are adding heat in order to make that happen, right? Because if I just put, like you said, we need fire, you said. And if I just put, you know, egg, salt, and oil in a bowl, it would not taste very good. So that's a type of reaction that needs heat. That's a great example.
I said like the combustion in a car, like when you drive a car and you turn it on and the gas, it's like gas, and then it becomes like, yeah, that's what I said.
Yeah, that's a great example. We're going to talk about combustion later today. So that's a perfect transition. Wow, someone put photosynthesis in the chat. What a coincidence, because that was the example I thought of. So I have some plants in my apartment, and so photosynthesis is a reaction where CO2 and water combine to make glucose and oxygen. So that's why plants are good for the air, is that they take carbon dioxide and they make oxygen. So in that case, my reactants are CO2 and water, and my products are glucose and oxygen. So I think a lot of us are familiar with various kinds of chemical transformations. We all sort of cook, and yeah, someone put breathing in the chat. That's a great example. You take in oxygen and you end up producing carbon dioxide. But I think it's worth kind of getting in the habit of when you see a chemical transformation, try to translate that into chemistry words in your head. What are the reactants? What are the products? Okay. So one of the most important facts for chemical engineering and engineering in general is that mass is not created or destroyed. It is conserved. And so a conserved quantity is something that is not created or destroyed. So mass is a great example. Mass can change forms in these reactions, but we're not getting rid of or creating mass. So reactions take place by moving electrons around. So when we talked about valence electrons making bonds, which are how compounds and molecules are made, those valence electrons can move around and change who they're bonding with. But the protons and the neutrons are not involved. So this is just changing the bonds between different atoms by moving those valence electrons around. But we're not changing anything about the nucleus of the atom, which contains the protons and the neutrons. So nuclear reactions involve the nucleus. And if you're interested in nuclear engineering, that's a whole field. You can study that. And you might talk about nuclear reactions at some point later in your chemistry class. But for now, we're not talking about nuclear reactions. It will be very clear at whatever point you start studying nuclear reactions. There will be a very clear transition. So unless you are in the middle of a unit where that's actively what you're studying, it is a safe assumption that the nucleus is not involved. And so if the nucleus is not involved, then the number of protons in any given atom isn't changing because protons are in the nucleus. And so what type of atom we have can't change. Does this make sense? We're only affecting which valence electrons are interacting with which other valence electrons. So the nucleus isn't changing, and therefore the atoms of a given element can't change. We still have to have the same number of each type of atom. We're just changing who they're bonded with. So if I have a reaction that I'm writing as reactants going to products, and there's 1 carbon atom, 4 hydrogen atoms, and 4 oxygen atoms on the left. I'm just making that up. That's just sort of, let's assume that our reactants have this many atoms. Then I know my products have to also have 1 carbon atom, 4 hydrogen atoms, and 4 oxygen atoms. They can be bonded in a different way to each other, but they must still exist. Does anyone have questions on this? So I'll just say it one more time. Because the nucleus isn't involved, the identity of the atom can't change, whether it's oxygen or carbon or whatever, because the number of protons defines what kind of atom we have. And so given that, the number of atoms of each element on each side of our reaction has to stay the same, because we can't create or destroy atoms without doing nuclear reactions, which we're not going to do. So as an example, hydrogen peroxide, which I'm just going to tell you is H2O2, so that's 2 hydrogen atoms and 2 oxygen atoms, is going to form water, which is H2O, and oxygen, which is O2. So if I explicitly draw out all my bonds, it's going to look like this. I have H2O2 on the left, that's my reactant, and it's going to react and form H2O and O2. So my question for you is, how do you feel about this reaction? Does it look good as it is, or is there something wrong that we need to fix? I'll give you about 30 more seconds to think about it. Okay, so about 70% of you think that something is wrong. Would anybody be willing to unmute and share what they think is wrong, or why they think it's fine, or send something in the chat? Yeah.
On the left side, there's 2 hydrogen and 2 oxygen, and then on the right side, there's 2 hydrogen and 3 oxygen. And they're supposed to be the same.
Exactly. So someone also said in the chat that there's an extra oxygen atom on the right. And so if I leave this reaction as it is, what I am saying is that I can take hydrogen peroxide and then magically create an additional oxygen atom. That would be catastrophic if that were true. So what that means is that on the left, there's 2 hydrogens and 2 oxygens. And on the right, there's 2 hydrogens and 3 oxygens. I have magically created a 3rd oxygen atom from thin air. That's bad. I can't do that. Or if I did, I would get a Nobel Prize. So with chemical reactions, we always just count the atoms themselves. So we're not worried about, well, chemical reactions have everything to do with who's bonded to who. But when we're thinking about conservation of atoms, we're just counting how many oxygen atoms there are on each side, how many hydrogen atoms. So when we count on the left and the right, they better be equal. So what I need to do is change how many of each molecule are on each side. So I don't want to change who's reacting. So I can't sort of add another species, but what I can do is change the amounts. So if I add a second molecule of H2O2 on the left, I still have the same reaction. I still have H2O2 forming water and oxygen, but I'm just changing the amounts. And so now I can redo my counts. So now on the left side, I have 4 hydrogens and 4 oxygens. So we're still not balanced, but we're getting closer. And so now I can look on the right side and say, okay, I need 2 more hydrogens and 1 more oxygen. That's perfect. I can just add another water molecule. And now I have 4 hydrogens and 4 oxygens on each side. So what I want to do is just change what number, how many of each type of molecule I have on both sides until I have the same number of each type of atom on each side. So now that I've done this, yay, my reaction is balanced, and I can write that as 2 H2O2 molecules react to make 2 H2O molecules and 1 oxygen molecule. So what we're doing there is called stoichiometry. So for those of you who hadn't done this in high school, that's what that word means. And then these numbers that indicate how many of each type of molecule we need, these are called stoichiometric coefficients, which is a big word that just means how many of each molecule do I need in order to make this reaction balanced so that I'm not creating or destroying any type of atom. So we're going to practice with this pretty much for the rest of today. So if it's not clear exactly how to do this, that's okay. We'll go through it more. But does everyone understand what we are doing and why we are doing it? Okay, so what these stoichiometric coefficients mean is that if I have 2 H2O2 molecules and they go through this reaction, I'll end up with 2 H2O molecules and 1 oxygen molecule. So the way that I think of this is when I'm cooking, I can't just throw a random amount of yeast and water and flour into a bowl and end up with bread. The amounts matter. And so that's what those stoichiometric coefficients are telling us. Okay, so some really common mistakes with stoichiometry. I'm going to put a giant red bar on the side so that whoever is watching this later knows that everything on this slide is bad. So you cannot do anything with an unbalanced reaction. So if you ever are asked to do anything with a chemical reaction, the very first step you're always going to do is make sure that reaction is balanced. Balanced meaning there's the same amount of each atom on each side of the reaction. So for example, if I asked you on a test, how many molecules of H2O2 are consumed per molecule of oxygen formed, It's not 1. This reaction is not balanced because I have 2 oxygens on the left and 3 oxygens on the right. So I can't interpret anything about the number of molecules involved in this reaction without balancing it. And then the other thing you're not allowed to do is change which species are involved in the reaction. So for example, if I'm balancing the same reaction we've been talking about, H2O2 goes to H2O plus O2, I cannot just say, well, I have 2 oxygens on the left and 3 on the right, so I need to add an oxygen on the left. This reaction that I've written in red here is balanced, but it's not the same reaction that I asked you about. So what I asked you to do was take this reaction, H2O2 goes to H2O plus O2, and you've given me this reaction, which is a totally separate reaction. So what you need to do is balance the reaction just by changing the coefficients, the stoichiometric coefficients, those numbers in front of each molecule. And then once you do that, you can interpret things using those numbers. So given this balanced reaction, 2 molecules of H2O2 combine to make 2 molecules of H2O and 1 molecule of O2. Then I know that 2 molecules of H2O are consumed for every molecule of O2 formed. So does everyone understand, or does anyone not understand what we're trying to do here? Okay. So I'm going to give you one more example that I'm going to walk through slowly, and then I'm going to have you guys practice. So here's a reaction. C6H14 reacts with oxygen O2 to form CO2 and H2O. So this is a reaction that I've written out in words. And so the first step that we always do is write it out as our chemical equation. So I have C6H14 plus O2 goes to CO2 plus H2O. And I'm leaving spaces in front of them to make room for those stoichiometric coefficients. Just so you know, someone mentioned combustion as an example of a reaction. It's a really important example of a reaction. So what a combustion reaction is whatever the thing that is being combusted. So in this case, it's C6H14. It reacts with oxygen to form CO2 and H2O. So if anyone ever asks you to write down the chemical reaction for the combustion of blank, the reaction is blank plus O2 goes to CO2 and H2O, and you have to balance it. So that's just a definition that you need to know. And I'm going to ask you to do that on the homework. So this is what that means. But for any reaction, combustion or otherwise, I'm going to write out the unbalanced equation. C6H14 plus O2 goes to CO2 and H2O. Then the next thing I'm going to do is count how many atoms of each type of element are involved on each side. So on the left side, I have 6 carbons in C6H14. I have 14 hydrogens in C6H14, and I have 2 oxygens in my O2 molecule. On my right side, I have 1 carbon atom in my CO2. I have 2 hydrogen atoms in my H2O. And then I have a total of 3 oxygen atoms. So I have 2 in this CO2 and 1 in the H2O. Does anyone have any questions on just how I'm counting those? Okay. So because these aren't equal on each side, I have 6 carbons on the left and 1 on the right, and 14 hydrogens on the left and 2 on the right, this equation is not balanced. I cannot use this reaction as it is. So what I need to do is adjust these coefficients until my counts for each element are equal on each side. So different people develop their own strategies for how they do this. As long as you end up with your counts matching on both sides, there's no right order of which element to balance first. What I find most effective is starting with the elements that appear the least frequently. So for example, if I started with oxygen, that'd be a little bit hard because I have 2 on the left and 3 on the right, but they're split up among these 2 different molecules. So there's sort of too many variables. It's hard for me to figure out what to do. So what I'm going to do is start with carbon. Carbon only appears in C6H14 and in CO2. So if I start with carbon, if I have one C6H14 molecule that has 6 carbons in it, then in order for the carbons to be balanced, I need 6 CO2 molecules. So now, if I totally redo my counts, because I've changed my number of CO2 molecules, nothing on the left side has changed yet. But on the right side, I now have 6 carbons. So that's nice, my carbons are balanced. But CO2 also has oxygen in it. So I need to change my count of oxygens too. So I have 6 CO2 molecules, each of which have 2 oxygens in them. So this, in my CO2 molecules, I have a total of 12 oxygens, 6 CO2s, each with 2 oxygens. So that's 12 oxygens, and I still have 1 in my water. So this is 13 oxygens on each side. Does this make sense? So far, this is still not balanced. Okay. So now my carbons are balanced. So I can kind of mentally put a check note next to the carbons for now. But my hydrogens and my oxygens are still not balanced. So I'm going to go to hydrogen next, just because it also only appears in 2 places. So it's still a little easier than oxygen. So if I have 14 hydrogens on the left and 2 on the right, so each H2O molecule has 2 hydrogens. So in order to have 14 hydrogens total, I need 7 H2O molecules. So on the left, I have one C6H14 molecule that has 14 hydrogens in it. And on the right, I have 7 H2O molecules that each have 2 hydrogens in it. And so that's also 14 hydrogens. But H2O also has oxygens in it, so I need to adjust my oxygen count too. So my oxygens, I have 12 in my CO2 molecules, 6 CO2 molecules with 2 oxygens each, and I have 7 H2O molecules, each with 1. So 12 plus 7 is 19. So now I have 6 carbons on both sides. I have 14 hydrogens on both sides. And so now only my oxygen is unbalanced. So if I change either of these coefficients, I'm going to screw up the carbon and hydrogen balance, because I can't change the number of oxygens on this side without also changing the number of carbons and hydrogens. But on this side, I can manipulate just this oxygen to balance the oxygen without screwing up the carbon and the hydrogen. And so what I'm going to do is, I know I have 19 oxygens on the right. So how many O2 molecules do I need in order to have 19 oxygens? 19 divided by 2 is 9.5. So I need 9.5 oxygen molecules. So now I have 6 carbons, 14 hydrogens, and 19 oxygens on each side. And my last step is to get rid of fractions. I can't have half an O2 molecule. So what I'm going to do is I'm going to multiply all of the coefficients by 2 so that this fraction goes away. And so I'm going to end up with 2, 19, 12, and 14. So that's just the previous coefficients all times 2. And adjust my counts. So now I have 12 carbons, 28 hydrogens, and 38 oxygens on each side. And so my reaction is balanced. Oops. My reaction is balanced, and I'm happy. And so I can use these coefficients now to learn that for every 2 molecules of C6H14 that I burn, that I combust, I make 12 CO2 molecules. So I can now use these stoichiometric coefficients to learn something about my reaction. Does anyone have any questions on what I did or how I did it? I'm going to make you practice in a minute. So now is the time. So is multiplying by 2 a rule whenever there's a situation like in the example? So here I had 9.5. So I had a half here. So I multiplied by 2 to get a whole number. If I had 9 1/3 for whatever reason, then I would multiply by 3. So you're just going to multiply by whatever factor you need to make sure you have whole numbers. So it's not always going to be multiplying by 2. You just want to end up with whole numbers so you don't ever have like 1/3 of a CO2 molecule, because what does that mean? What does it mean to have 1/3 of a water molecule? That's a great question. Any other questions? Okay. So I'm going to have you practice with these reactions. So we're balancing each of these reactions, which means we're doing what I just did. We're manipulating the stoichiometric coefficients on both sides to make sure the reactions are balanced. And as a reminder, I defined what combustion means on the previous slide. So combustion of C6H14 was C6H14 plus O2 goes to CO2 and H2O. So you can figure out what the combustion of CH4 means using this. Does anyone have any questions on what you're supposed to do? Okay. I'm going to send you into breakout rooms. I'm going to give you kind of a long time. I'll pull you back in at 11:30. I want you to have enough time to practice. But if you finish early, feel free to come back. But do work together in your groups and make sure you all agree on what the coefficients are before you come back. Okay? Okay, if you're watching this recording later, now's a great time to pause to practice. I'm going to give everybody 30 seconds or so to come back into the main room. How did that go, y'all? How are we feeling?
Pretty good, pretty good.
Awesome. Almost everybody's back. Give it just a minute. Okay. Cool. So I'm just going to go over the solutions here. So for H2 plus O2 going to H2O, we have 2 hydrogens on the left and 2 on the right, but 2 oxygens on the left and 1 on the right. So what we can do is put a 2 in front of the H2 and a 2 in front of the H2O. So now we have 4 hydrogens on each side and 2 oxygens on each side so that it's balanced. For CH4, the combustion reaction is always CH4 or whatever thing is being combusted plus O2 goes to CO2 and H2O. And so when we balance that, we get CH4 plus 2 O2 goes to CO2 plus 2 H2O. For this reaction here, we end up with P2S5 plus 3 PCl5 goes to 5 PSCl3. And then for the last one, we end up with 4 Fe2P plus 18S goes to P4S10 plus 8 FeS. So what's really great about stoichiometry is that it's really easy once you're done to know whether you got the right answer or not. It's very easy to check your answer because all you have to do is count the number of atoms of each element on the right side and the left side. The whole process of stoichiometry is kind of iteratively changing those coefficients and until you have that balanced. So it's not necessarily easy to figure out which coefficients to change in which order, but once you're done, you should always be able to check that your answer is right because there should be the same number of atoms of each element on each side. Does anyone have any questions on conceptually what's going on here? There's a lot more practice with this on the problem set 7, and you'll get more practice with it in Chem 1A as well. But if you hadn't heard of stoichiometry in high school, this is all it is. That's all there is to it. It's just balancing reactions. The couple other things I wanted to talk about today. So if you know the phase of the molecules, so solid, liquid, gas, you should include it. So for example, P2S5 is a solid, PCl5 is a solid, and PSCl3 is a gas. So you wouldn't be expected to just know off the top of your head that P2S5 is a solid. But if you know it, if you're told it, this is how you denote it on your reactions. So if you see an S or a G or an L written after the species in your reaction, it's just indicating the phase. So it doesn't change how you balance it or what you do. It's just giving you extra information about the species that are involved. And then the ones that aren't shown in this particular example is L means liquid and AQ means dissolved in water. So for example, salt, NaCl, is a solid, or it can be dissolved in water. So it's not a liquid because by itself, it's a solid, but I can dissolve it in water. So if I have NaCl or table salt dissolved in water, that's part of my reaction, I would write AQ. I once had a student who I asked them to write the combustion of a species. And they were like, well, I didn't know the phase of CH4. So I just didn't write the reaction because it's not complete without the phases. So always include the phases if you know them, but if you don't know them, like still continue with the problem. It's great to include them if you can, but if you don't know the phase or can't figure out what the phase will be, like that's okay. It's just extra information that you should include if you can. And then the other thing that I want to talk about is catalysts. So there's there are multiple whole fields of science devoted to catalysts. So we're not going to try to like fully understand everything about catalysts and how they work. But the most important basic thing is that they increase the rate of the reaction. So they make the reaction faster or more efficient without actually being consumed or produced. So just by being there, they don't participate in that they're not consumed, they're not reacted, and they're not produced, but they speed the reaction up. So for example, SO2 and O2 combine to make SO3, but only in the presence of this catalyst. And so if we balance that reaction, we could say that 2SO2 plus O2 plus V2O5 goes to SO3 plus V2O5. And so that V2O5 catalyst, because it's not either consumed or produced, if it's there at the beginning, it's still there at the end. And so we can cross those out because they're present on both sides. It's not a reactant and it's not a product. It's just there to begin with and there at the end. And so the way that we denote that is we put it on top of the arrow. So just like some reactions need heat to proceed, some reactions need a catalyst to proceed. So if you see a species written on top of the arrow, that means that it's not either consumed or produced. It just needs to be there in order to make the reaction go faster. Does this conceptually make sense? Okay. So one way you might see this drawn is with what's called an energy coordinate diagram. So going back to our example of H2O2 forming water and oxygen, we balanced it this way. We draw an energy coordinate diagram like I'm showing here. So the y-axis is energy and the x-axis is reaction coordinate. So you can think of that just as our reaction proceeds from right to left, we go from reactants to products. And so in this case, the reactants have higher energy than the products, but it's kind of hard for all of these molecules to find each other and go through some intermediate phase to end up at the final product. So if there wasn't a catalyst, the transition state would be really high energy, and high energy generally means less favorable or less easy to achieve. So I think of this as like climbing a hill. And so these reactants have to climb a really tall hill in order to get to roll down to the other side at the end. And so maybe this transition state, again, there's like a whole field of trying to figure out what the transition states are and what they look like. So you can't, it's very hard to look at a reaction and know what the transition state will be. So don't worry about trying to like figure out where this line is or anything, but just think about it conceptually. If there is a catalyst, then this hill that our reactants have to climb can become a little less steep. So if there's a catalyst, then maybe those atoms can temporarily bond with the catalyst so that their intermediate state is less difficult. And they're still going to end up at the same final products. So this catalyst, this MnO2, isn't actually consumed or produced. It doesn't change the initial state or the final state. It just changes. It's just a little shortcut around the hill that the molecules need to climb. So again, for right now, I wouldn't worry about where these lines are or what the transition states are or exactly the mechanism of how the catalyst is working. But just think of it conceptually. The things you need to know about catalysts are they aren't created or consumed. So they're there at the beginning and they're still there at the end. Their bonds haven't changed at all. But in the middle, they make the transition state a little happier so that the reaction is easier to proceed. So they just make that hill that our atoms have to climb a little less steep. Does this make sense conceptually? So when you have a catalyst, it is involved in the intermediate state, but it doesn't actually change from the beginning to the final state. And so just to indicate that it's there and it's helping, we put it above the arrow. So I think the thing that you would need to be comfortable with is if you see a reaction written like this, you would need to know that MnO2 is a catalyst. Okay. So there's lots of practice on problem set 7 with balancing reactions and with interpreting how we've written reactions and stoichiometry. There's also practice with interpreting line drawings as part of it. So that's all I wanted to go through today, but I wanted to leave time at the end because I think people had questions on line drawings. So if you want to stay after and talk about line drawings, please do, or if you want to stay after and talk about anything else. But other than that, that's all I've got for today. And please let me know if you have any questions.